My name is Dane Larsen. I was the financial manager, oversaw the schematic and drafting as well as the tablet design. Zainab here was the hardware manager, oversaw the design and development of the stylus. And Tarek was our technical manager, who oversaw the algorithm development and was also our software design, oversaw the software design. On a side note here, two of us will be entering the professional realm, and the other two will be entering or continuing their pursuits in academia. Identity fraud has become a huge concern for us as consumers in this day and age. As we are all familiar with, we usually use electronic transactions on a continual basis. 9.9 million Americans have been affected by identity fraud, and this accounts for $48 billion in lost revenue. Now, 43% of these occurrences are caused by some sort of lost wallet or stolen credit card, and this accounts for roughly $20 billion in losses. As you're all familiar with, at a grocery store, there's an electronic prompt that you use to sign off when using your credit card. Now, currently the banking system has no protocol to verify these types of signatures. And because of this, there's a huge security risk for each consumer. Now, we have developed certain project objectives during this design here. And the first objective was to design, develop, and test a prototype. We wanted to gather certain aspects of a signature, and the aspects that we chose here were the image, the pressure, and the speed of the signature. Now, the second objective here was to collect and analyze this biometric information. The way that we collected the pressure was through a custom-built stylus. We also wanted to process this information for verification reasons through MATLAB. And we also wanted to gather this information and compare it for verification purposes to corresponding information stored in the database. Now, the third objective here was to inform the user whether this signature is authentic or whether it is fraudulent. Now, on a top-down approach here of our design here, as you can see here on the left-hand side, we have the stylus and the touchscreen. The stylus would collect the pressure, and the touchscreen would collect the XY coordinates of this signature. Now, this analog information will be fed into the microprocessor for AD conversion and fed into the computer for processing. Here on the software design part of this project here, we have the enrollment phase and the verification phase. Now, right here in the enrollment phase, a signee would input his signature multiple times and determine a certain threshold. Now, this data would then be stored in a database for verification purposes. Now, in the verification mode here, we wanted to compare the image, the pressure, and the speed of this signature, as mentioned before. Now, this information would then be compared with the corresponding information in the database previously stored. Now I'm going to turn the time over to the rest of my group here, who will go over each aspect of this project in more detail.
Thank you. So our hardware main purpose was to capture the unique biometric features of each signee. And in order to do that, we needed the signature image and the pressure. We collected the signature image using a tablet, and the pressure applied while signing using a custom-built stylus. This information was collected and sent to a microcontroller. While doing our research, we found out that there were two main touchscreens in the market. There was the capacitive and the resistive. We decided to go with the resistive one mainly because of the following criteria. It has a faster response time, it was cost-effective, and its accuracy was very comparable to the capacitive one. In addition, it does not require any conductive object to sign on it. Therefore, we decided that it was a better choice to go with. Our second main component of the hardware is the stylus. It was custom made. We implemented the pressure sensor at the end, and we modified the interior in such a way that there is a moving rod. So whenever you press the stylus on the tablet, the rod moves accordingly, and this generates a pressure signal. This signal is amplified before being received by the microcontroller. This is our overall final hardware schematic, and as you can see here on the left, we have the pressure sensor sending the pressure information. We collect the X and Y positions from the touchscreen, and we have the microcontroller converting the analog signals to digital. The main aspect of our hardware is the fact that it is portable. It only runs on a 5 volts that is supplied by the USB connection to the computer. So as I just said, we get the X, Y, and pressure information from the tablet and the sensor. Those signals are converted from analog to digital by the Arduino. Our choice of the Arduino was based on the fact that it is cost-effective, it was easily programmable, and it offers a high sampling rate of about 140 samples per second. Once the data gets into the computer in this manner, X, Y, and pressure of every point being touched, it is picked up by MATLAB for further processing. And I will let Bassam let us know more about that.
Thank you, Zainab. Now that we're able to receive all the data through MATLAB, we go into a pre-processing stage. So at this point, we look at the number of panelists that the user applies, and this allows us to break the signature into segments. As you can see on the picture over there, each segment is in a different color for visual purposes. We also get rid of the initial and the final point. The reason so, we're using a resistive tablet. So right at the beginning, when they're about to put the stylus on the tablet, and when they're about to release, we don't get accurate voltage readings. So we decided to just omit those for future processing. We also have an error correction algorithm, and this allows us to reconstruct the signature in case there's a distortion. And we have a picture over here before and after the algorithm is applied. And for noise reduction, we applied a software smoothing filter. We had a choice between hardware and software. We decided to go with the software one because it's cost effective and it has a less quantization error. And now everything is going to be communicated back to the user via a very friendly graphical interface. On the top left, you can see the file tab where you can create, save, or delete users. We also have an enrollment tab, so you can switch between the enrollment or the verification mode. And you're also able to see the signature and see the X position, the Y position, and the pressure readings as well. On the right-hand side, you get to see the correspondence information that are stored in the database that we collected during the enrollment phase. And on the further right over here, these are the values of how well your signature matched our database. So during the enrollment phase, we go through the data acceptance phase. Basically, we ask you to sign once and twice and 3 times. So the first signature is always taken. The second and the third, we check for the number of segments and the timing. Once MATLAB approves that, your signatures are taken. We move into the averaging mode. At this point, we're going to average the 3 together, but we need to make sure they're all of the same size. So we interpolate or decimate accordingly. Now we're ready to move into an autocorrelation phase, and we basically ask the user to sign against themselves. This allows us to learn about their features, and it allows us to set up certain thresholds as well. And we're going to use that for our verification purposes. So during the verification mode, we go through the same routine where MATLAB will check for the number of segments, will check for the timing. Once it's approved, it moves into a verification algorithm. At this point, we're ready to compute the correlation values of the X position, the Y position, the pressure as well. And we calculate the height width ratio percentage difference as well. We also had a velocity ranking algorithm. Unfortunately, during the testing part, we found out it holds no value, so we omitted it from our final decision making. Now that we have all the necessary numerical analysis done, we're ready to dump it into a final decision algorithm, which Tarek will go in further detail and explain. But before we do so, I just want to give you an overall plan of our testing. We basically broke it into 3 stages. In level 0, we assume that the forger has access to a credit card that only has a name on it. In level 1, we assume that he has access to a credit card with the name and the actual signature of the image. And in level 2, we assume he has access to all the necessary information so he can get the forgery done and break into the system. So we're provided with the timing, with the number of segments, with the height to ratio, with the pressure readings, and the XY position as well. This is just a sample of how we conducted it. This is the verification part for the actual user, and then we have the verification part for the forger so we can get our results. Tarek can take it from here.
So as Bassam stated, when the data first comes into the system, there's 2 main caveats in which we can immediately detect forgery. The first is if the user signing is forging and they use the wrong number of sections to your signature. The next thing that we can check for is the length of each one. If one of the lengths of any one of those segments is wrong, they hesitated for too long while signing your signature, which is a noticeable difference from you signing against yourself. Assuming at this point the signature passes through this phase, we compute the following values. The idea now is to use these values to try to differentiate between a valid signature and a forgery. We're going to do this by taking each one of them and multiplying them by the amount of information content they have, adding these together to create one final score. This score is going to be the metric we use to determine whether the signature is valid or forgery. And then the question becomes, how do we determine this weighting vector? How do we know which one of these components holds more information than others? What we did was we took our enrolled users and we plotted their data in feature space. What you see here in the blue stars are their scores in 3 dimensions with Y correlation, height-to-width ratio, and pressure. The clustering of them says that people generally score very well against themselves. In red stars, you see people's forgery attempts against these users. What you'll notice is that the red stars may score just as well in 1 or 2 of these dimensions, but not necessarily all of them. Therefore, with appropriate weightings, we can separate these into single numbers. So how we did this? We took both sets of data, true scores and false scores, and we tried different weighting vectors to try to manipulate this data down to 1 dimension as far apart from each other as we can. What we ended up learning was that X correlation held the least amount of information. Anyone who signs a signature left to right has almost the same waveform, therefore it's very easy to reproduce. So we gave this 5% of the final set. Height-to-width ratio, we gave 10%, followed by pressure at 15%, and Y correlation at 70%. If you look at Y correlation, the Y motion of your hand while you sign your signature turns out to be the hardest part of a signature for a forger to reproduce at the same speed that you do yours naturally. So taking our algorithm here into 2 stages, the first being what Bassam defined as database acceptance, and the second being his featuristic approach, where we can present our results to you. Looking at level 0, where the user has a credit card with only the front information, so just the name and text, we stopped 100% of the people in the first stage on just speed and the number of sections. Going to level 1, where the user would have taken a credit card and has access to the front and the back, which would be a real-world scenario, 87% of people, or 26 of 30, were stopped in the first stage. Of the 4 that moved on, an additional 2 were stopped using this feature detection. One thing to note here, though, is that of all 4 signatures that made it past stage 1 into stage 2, they were single-section signatures. If any signature that went into our system had more than 1 segment to it, such as a first and last name sign, they were immediately detected in stage 1. In level 2, which was this omnipotent state of knowledge for the forger, we gave 12 of 30 people got stopped in the first stage. Of the 18 that moved on, an additional 15 were stopped based on features, as they correlated very poorly, but their timings were good enough to match. This 90% was the hardest situation for our system to stop, therefore we'll explore that in slightly more detail. Here, using the weighting vector we discussed earlier, we've mapped from 4 dimensions, or the 3 plotted, down to 1, and you can see in blue, as the circles go, the actual score that the user scored in their database. In red, you see forgery attempts against them. Green determines a threshold, which is 10% less than the blue line. If the red line, a forgery attempt, crosses the green line, they're considered a forgery as accidentally accepted as true. In determining this threshold, one thing we kept in mind was we wanted to minimize the number of forgeries that got accepted as being true. We also, on the other hand, had to allow a low false rejection rate. Our false rejection rate turned out to be 8%. So with this set at 10%, every 100 signatures you sign against yourself, you pass 92 of them. Our system in total came out to cost about $426. A single unit, however, would cost $126 to build. However, a lot of that is actually shipping and handling. As a group, we spent 1,230 hours on the project. If our department decided to pay us $25 an hour, that would cost them slightly less than $31,000 to design the system beginning to end. Lessons we learned throughout the semester was to select a good team, and we felt very fortunate in that regard that our team, we communicated effectively together. Get your advisors involved early and often. Whenever you see a problem might come up, go to them, their doors are open, as well as just if you think you need a direction to move in or you feel lost, they were also there for that. And obviously, as I just mentioned, order more parts than you need, as buying a 10-cent capacitor and paying $15 to ship it is not very wise. We'd like to acknowledge our advisors, Dr. Economy and Dr. Cook, for all of their help. We'd like to thank Dr. Nelson, we'd like to thank Mohammed G, and Dr. Lloyd for all their input throughout the semester. We'd like to thank Emra, who is one of our forgers. He was very talented in forging. And we'd like to thank all of the volunteers for their enrollments into our system. And now we'd like to open this to any questions.